Hi guys, I bet you thought you're gonna miss me. You all miss me. Good luck to me. This is my first video that I'm doing, so it might be rough. But hey, we'll get some stats in. So get your notes out. Let's do 3.2 least squares, regression line, and residual plots. So I'm gonna go through the PowerPoint with you guys, and hopefully this works. And then we'll do questions when I'm back on Tuesday. So here we go. So hopefully you guys are going to be able to calculate residuals, construct and interpret residual plots by the time we're done with this today. So residual plots, guys, you're going to want to be able to do this on your calculator, as always with stats, on your calculator. So residuals, in most cases, no line will pass exactly through all the points in a scatter plot. So you guys know that when you put your line of best fit or your linear regression, that line does not fit all of the points. We do the line that fits the best. So we use residuals um, to give us a little bit more information about what's happening. So a good regression line makes the vertical distance of points from the line as small as possible. So we want these black lines to the red dots to be as small as possible. So to find a residual, you're going to do the predicted minus the you're going to do the observed minus the predicted. So observed is like what you got in your study. And remember, y hat comes from that prediction equation. Okay. So your residual is actually the distance from that point to this line. It's a distance. Okay. Negative residuals are going to be below the line. That makes sense. And positive are going to be above it. Okay, so the least squares regression line produces multiple different residuals. The line of y on x is the line that makes the sum of the squared residuals as small as possible, okay? So again, here's our backpack that we talked about, backpack weight versus how heavy someone was. This guy over here, remember from our example the other day, was an outlier. So let's calculate some residuals. So go ahead and open your books to page 168. I'm going to get there too. And we're going to go back to the backpacker's problem. So the problem is find and interpret the residual for the hiker who weighed 187 pounds. So when you look at what I have, the table here on the PowerPoint, you have your body weight up here and you have your backpack weight here. So to find and predict, the regression line is going to predict our pack weight. So that's that y hat equation. And if you look in your books, the equation is there. But if I pull it up and show you guys, your prediction was actually your y hat, which was your pack weight, and don't make fun, I'm writing with my finger, was 16.3, that's a point, plus your 0.0908, and they plug in their backpack weight of 187. And so they get that y hat is going to be about 33.28 pounds. Okay. So for this hiker, the actual pack was 30 pounds. So calculate the residual. So if we go back to here, they're telling us that y is actually 30. So our line, our prediction equation, told us that they should be able to carry this amount right here. And in reality, this is actually what the person carried. So if we go back to our equation for the residual was y minus y hat. So they're asking you to do 30 minus 33.28. Okay, and that of course is going to give you a negative 3.28. And I'm running out of room here because my fat finger, it makes it hard to write. Okay, but more or less that is the regression line over predicted how much that person could carry. Okay, so let's go ahead and calculate residuals. We did that one already. You don't have bell work right now. So let's go ahead and figure out how to do this on our calculator. So in your calculator, make sure all of your Y's are turned off. So all of your Y's are going to be turned off. If you go to your calculator, let me show you how to do that. So here's your calculator. If you turn it on and go to your Y equals, either make sure you don't have anything in here or that the equals is not highlighted. If it's highlighted, it's on. So if I had an equation in there like 2, do you see how the highlight is there? You need to click on that and hit enter. And that will turn it off. I would just recommend clearing those out so you don't have to worry about it. Okay? So go ahead and enter this information. Enter your NEA change and your fat gain into your 2 different lists. And the sub might have to pause it right now to give you guys time. I'm going to keep moving on as if you have that already in your calculator. But enter it into your list. And then you're going to perform the following steps like you guys have been. You're going to add one part to it though. So you guys have already been doing Lsrl. You've already been finding your residuals. But at the end of this, you're going to do L1, L2, Y1, which is your Y1s found in your vars, YVARS 1 function. So your vars, YVARS, number 1, which is the function, and I guess I'll show you guys that on the calculator here. Let me get out of here. So vars over to YVARS, either hit 1 or down to function and hit enter. And then you want it to store your equation in the Y equals 1. So you're going to hit enter there. Okay, and I was already in here, so it didn't save it in the right place, but that's where you're going to put it in your calculator. Okay, that's going to store the equation of your line for your residual plot in your calculator. So now go ahead, when you plot, your scatter plot like we've done for the last 2 days in class. Your Y equation should be turned on now, so it should put your linear regression line in your data, which is what you're seeing on my screen right now. Okay, remember zoom 9 fixes everything. So if you get a funky graph, hit zoom 9 and see if it fixes it. Okay, we use our calculator like I told you the other day to find the least squares regression line, but you need to be able to find the slope and the y-intercept also if given just some random data. So you need to know these 2 equations. The slope, which is going to be your coefficient of correlation coefficient, the R that we've dealt with, the standard deviation of your response or your Y, and the standard deviation of your explanatory or your X. The y-intercept you're going to find by is A equals, and you're going to do y bar minus b times x bar, which we're going to talk about here in just a second. So turn to page 173 and look at the example fat gain and NEA. So A says find the equation of the least squares regression line for predicting fat gain from NEA change. Show your work. So let's go ahead and do this. So let me see if I can actually pull up a clean sheet here. Look at that. That was me practicing. It was pretty awesome, huh? So let's do A. So A says find the equation of the least squares regression line for predicting fat gain. Change show your work. Well, in the equation, if you guys, I'll give you, your substitute's going to want to pause here and let you read the example on page 173. So I'll give her a second to do that. And now that you guys are back, for A, the least squares regression line of the fat gain, X has a slope. So you're going to use the equation that we just learned. B equals R SY over SX. Okay, and they gave us all of that information. They gave us the R. The R was negative 0.7786. And they gave us both of our standard deviations, the 1.13, and you should not round until the very end, but because I'm running out of room, I'm going to round right now, but do not round until you have your final answer, okay? 257.66. And when they simplify that, they get that their slope is negative 0.00344. Okay? And to find the equation of our line, we also have to have our A. So to get our A, we have to use our equation that they gave us for that. So to find the y-intercept, we're going to use the fact that the least squares regression line through x bar, y bar. So we're going to use y bar equals a plus bx bar. And we're going to use our y hat, which they gave us. I'm sorry, not y hat, y bar, which they gave us is 2.388. And we are looking for A, so we don't have that to plug in. B, they gave us, dirt, we found that. So that's going to be your negative 0.00344. And they also gave us our X bar, which was 324.8. Okay, and when we come up with that, we get that A equals, because of course I have to solve this algebraically, but we all know how to do that hopefully at this point. So I'm not going to spend time in this lesson doing that. We get that A is 3.55 kilograms. Okay, so, oops, I didn't mean to do that. I meant to hit that one. So the equation for our line is going to be y hat equals 3.505 minus 0.00344 x. Okay. If we move on to B, B says an NEA increase of 257.66 calories is a 1 standard deviation increase. Well, the question was, what change in fat gain does the regression line predict for each additional 257.66 calories of NEA? Well, our B equation, actually I'm just going to do a new sheet. Our B equation was B equals R times SY over SX. And so we've been given a bunch of this information. So B equals, we know what R is, they gave that to us, a negative 0.7786. And our standard deviations they gave to us, but calories they gave to us, that was our SY was calories. And our SX was actually our NEA. So our calories is going to stay the same. they're asking us about the S sub x. And they're asking us about the standard deviation of 257.66, which is our standard deviation. So if we're at 0 and we go out to 257.66, we've only gone out one standard deviation away. So that's actually going to be a 1. So when we multiply this, we actually get that B equals a negative 0.89. So the regression line predicts a decrease of 0.89 kilograms in fat gain for an additional 257.66 calories of NEA. Okay, so let's go back to our PowerPoint here. I'm kind of flying through this. I want to make sure you guys have time today on your practice. So residual plots. So far we've talked about how to find a residual. So far we've talked about how to find a slope and a y-intercept, given some information and not using our calculator. So one of the first principles of data analysis is to look for an overall pattern and for striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between two variables. We see departures from this pattern by looking at residuals. Departures is just another fancy word for outliers. Okay, so a residual plot is still a scatter plot, which we've been doing for days, except for it's going to be the x-axis is going to be the residuals, and the y-axis is going to be what was originally your explanatory variable in your original scatter plot. Residual plots help us assess how well a regression line actually fits our data. Okay, so here we have A. This is a scatter plot. It has that line of best fit that you guys are coming to learn, known as linear regression. Okay, so what they've done is they found the residual of every single one of these points here. So this point was an observed point, and it has a point on this line that is an expected value for it. So they subtracted those. So they did that for every single blue dot that you can see on the screen right now. And then they graphed it again, but notice the residual is going to be on the y-axis, and the explanatory is on the x-axis. Okay, the residual is never going to change. 0, you're always going to see a line straight at 0. That would mean that your prediction equation gave you exactly what you observed when it happened in real life. Okay, so there's the difference between just a scatter plot or a linear regression line and a residual plot. Okay, so they're both scatter plots. The residual plot is just a scatter plot of the residuals. So let's look at page 175 on your book. Here's another example of what we were just talking about. The two graphs that I just showed you for your residual plot and your scatter plot with your linear regression on it. A note about linear regression. If the regression line captures the overall pattern of the data, there should be no pattern in the residuals. So if this line here, this blue line, captured the true pattern of the red dots, there would not be a pattern at all over here in your residual. So notice that this blue line is not a good fit for this data. This is a curved line. Linear does not help us at all. So we know that is true because when we look over here at the residuals, we get this parabola looking thing. We get a pattern. It's a very distinct pattern. So that tells us that that blue line was originally not a good fit. Okay, so things to look for when you're examining a residual plot, and this is in your book on page 176. The residual plot should show no obvious pattern, which we just talked about. Look at the residual plot on page 177 and notice the increasing spread. I guess I should give you a second. Look at the page on 177. Okay, notice the increasing spread about the regression line as x increases. Notice how it kind of cones out, right? It's kind of close to the line and then it flares out. Y predictions for this line will be less accurate for larger x values, okay? The residuals should be relatively small in size. That's the next thing you would like, okay? So interpreting residual plots. A residual plot magnifies the deviations of the points from the line, make it easier to see unusual observations and patterns. So number one, the residual plot should show no obvious patterns. We talked about that, okay? This is no good. This shows us a pattern that tells us that the original line over here is not good, okay? The residuals should be relatively small in size. You want them to hug this blue line. Whoops. You want them to hug this blue line as close as possible. We've talked about that, right? So the next thing you need to be able to talk about is your standard deviation of the residuals, okay? So this equation does come up on your formula sheet, okay? And it also comes out in a lot of computer outputs. You just need to be aware of it, okay? This right here is the sum of your residuals, which you get by doing your observed minus your predicted squared, and then you divide it by your sample size minus 2. Again, calculator is going to give us most of this, computer output is going to give us most of this. You need to be aware of the equation. Okay, so r squared, this came up in our video the other day. R squared, the standard deviation of the residuals gives us a numerical estimate of the average size of our prediction errors. There is another numerical quantity that tells us how well the least squares regression line predicts values of the response y. So you could find this r squared value by doing 1 minus, and this SSE, that's the standard deviation of your least squares. Okay, so the coefficient of determination r squared is the fraction of the variation in the values of y that is accounted for by the least squares regression line of y on x. We can calculate r squared using the following formula. You can, or you can put it in your calculator. Your calculator has been giving it to you for days. The only time you wouldn't be able to use your calculator is if they don't give you the data, but you would need most of the data to plug it into the equation anyways. So your Lsrl, where you've been finding r, right above that you'll find r squared. So just put it in your calculator and use that function. Okay, r squared is useful because it tells us how much better the least squares regression line does at predicting values of y than simply guessing the mean for y for each value in the data set. So look at page 179. You should already be there, hopefully, or you were on 177. So get to 179. If we needed to predict the backpack weight for the new hiker but didn't know each hiker's weight, we could use the average backpack weight as our prediction. Okay. So if we use the mean backpack weight as our prediction, the sum of the squared residuals is 83.87. So they're squaring their residual, okay? If we use the least squares regression line to make our predictions, the sum of the squared residuals is, okay? And then we just use our equation. We're going to divide these two and we get this. So therefore, 36.8% of the variation in the backpack weight is unaccounted for by the least squares regression line. If we do 1 minus that, we get 0.632. So 63.2% of the variation in backpack weight is accounted for by the linear model relating backpack weight to body weight. Okay, so that is all we're going to do today. We are going to go ahead and look at computer output when I'm back on Tuesday. So you are going to do tonight's homework. I have left that for your teacher. Let's see if you can get back to my face. I'm not sure if you can. Oh, there I am. I did a wonderful job. Applaud. I'm sure you guys are all laughing since you're always just, you know, talkative and joyous first thing in the morning. But your homework is on your calendar. You were going to find it on Friday the 19th. We've actually fallen about a week behind now, but You'll find 3.2 on your calendar on Friday the 19th, or it is on the backboard wall. And I have also left it for the sub. So if you really can't figure out those two things, you can go ahead and ask her and figure that out. So you guys have a good weekend. And if you get stuck this weekend, you can always pull me back up. I have Stacy Magruder's channel now on YouTube. You can pull this video up and look at it again if you have questions. But you guys have a good weekend. We'll see you on Tuesday.